0D materials, nanoparticles, and quantum dots, properties and applications. Imagine shrinking matter so small that its properties begin to defy common sense. A red substance turns blue. A material that normally conducts electricity becomes an insulator. At this size, materials no longer behave like their bulk counterparts. They enter a strange and powerful realm of quantum effects, a realm where electrons are confined, energy becomes discrete, and surface effects dominate. Welcome to the world of zero-dimensional, 0D materials, nanoparticles, and quantum dots. But what exactly does zero-dimensional mean? It may sound abstract, but the idea is simple. In 0D materials, all three spatial dimensions are confined to the nanoscale, typically under 100 nanometers in size. These are not thin films, 2D, wires, or bulk solids, 3D. They are tiny, point-like objects, like islands of atoms suspended in space. Because of their size, electrons inside them have nowhere to go, and this confinement gives rise to extraordinary physical and chemical properties. Let's begin with nanoparticles. These are ultra-small particles of metals, oxides, semiconductors, or polymers. Gold nanoparticles, for example, can appear red or purple depending on their size, not because of pigments, but because of a phenomenon called surface plasmon resonance, where light interacts with the collective oscillation of electrons on the nanoparticle surface. Change the size or shape of the particle and the color changes. That's why gold nanoparticles are now used in biomedical imaging, sensors, and even cancer therapy, where they can absorb light and convert it into heat to kill tumor cells with precision. Now, let's zoom in even further to quantum dots. Semiconductor nanoparticles, typically just a few nanometers in diameter. These dots act like artificial atoms. Because their electrons are trapped in such a small space, they can only occupy specific energy levels, similar to how electrons in atoms are restricted to shells. When quantum dots absorb energy, they re-emit light at very specific wavelengths, depending on their size. A smaller dot emits blue light, a larger one glows red. This size-dependent photoluminescence makes them ideal for applications like display technologies, QLED TVs, bioimaging, and quantum computing. Have you ever seen a smartphone screen that seems unnaturally vibrant? Or medical images that show glowing tumors in exquisite detail? There's a good chance quantum dots are behind that. Their brightness, tunability, and resistance to photo bleaching make them far superior to traditional dyes in many cases. And because they can be engineered atom by atom, scientists can fine-tune their properties for very specific needs, such as tagging individual proteins in cells, or transmitting secure signals in quantum communication systems. But these materials do not only excel in optics. 0D materials also show unique electronic, magnetic, and catalytic properties. Iron oxide nanoparticles, for example, can act like tiny magnets and are used in magnetic resonance imaging, MRI, and drug delivery. Silver nanoparticles show strong antibacterial activity, which is why they are used in wound dressings and coating. In catalysis, nanoparticles offer high surface area to volume ratios, making them exceptionally efficient in reactions such as those in fuel cells or pollution treatment systems. And the story is just beginning. Researchers are now exploring quantum dot solar cells, where these dots harvest light more efficiently than traditional materials. In quantum computing, single photon sources based on quantum dots may one day form the building blocks of ultra-secure communication networks. And in medicine, multifunctional nanoparticles that combine diagnostics and therapy are being developed to seek out and treat disease in a single platform. Yet, as with any new technology, challenges remain. Toxicity, stability, and scalability are major issues, especially for biomedical applications. Many quantum dots contain heavy metals like cadmium, which require safe handling. New research is focusing on eco-friendly alternatives such as carbon quantum dots or silicon-based systems that maintain the desirable properties without the environmental cost. So, what makes 0D materials so exciting? It is not just their size, it is how their smallness unlocks a new set of rules. In these tiny particles, matter behaves differently. Properties become tunable, customizable, and radically more versatile. As we continue to learn how to control atoms and electrons at this scale, nanoparticles and quantum dots may become the key components of next-generation technologies, from personalized medicine to quantum internet. What if we could engineer materials that change color with a thought, or target only diseased cells, or compute using single particles of light? With zero-D materials, such visions are no longer science fiction, they are rapidly becoming science fact. Zero-dimensional, zero-D materials, such as nanoparticles and quantum dots, are nanoscale objects confined in all three spatial dimensions, meaning their electronic, optical, and mechanical properties differ dramatically from bulk materials. These materials typically range from 1 to 100 nm in size, and size-dependent quantum confinement effects dominate their behavior, while surface atoms represent a significant fraction of the total, making surface chemistry critically important. Cadmium selenide, CDC-CS, quantum dots change color based on particle size due to quantum confinement altering their band gap. It's like tuning the pitch of a flute by shortening its length. The smaller the quantum dot, the higher its optical note. Quantum dots exhibit discrete energy levels due to quantum confinement, similar to atoms, rendering their optical and electronic properties highly tunable with size. Smaller dots have wider band gaps, emitting higher energy light, while larger dots emit lower energy light, making them ideal for applications requiring precise spectral control. By adjusting synthesis time, researchers can create quantum dots that fluoresce from ultraviolet to near-infrared for bioimaging. It's like choosing marbles of different sizes that glow in different colors when exposed to UV light. Each size sings a different wavelength. Because of their high surface area to volume ratio, zero-D materials are highly reactive and prone to aggregation or oxidation unless stabilized. Surface functionalization by attaching ligands, surfactants, or polymers enhances dispersion, stability, and selectivity for targeted applications, and functional groups mediate interactions with environments such as biological fluids or electronic interfaces. Gold nanoparticles coated with polyethylene glycol PEG remain stable in blood plasma and avoid immune clearance in drug delivery. It's like dressing up tiny particles in raincoats so they can move freely through different weather without clumping or dissolving. Quantum dots possess unique optical properties, including high photoluminescence, quantum yield, resistance to photobleaching, and narrow emission spectra that make them powerful alternatives to organic dyes in imaging, sensing, and light-emitting devices, and they exhibit phenomena such as blinking, multi-photon emission, and single-photon emission. In cellular labeling, quantum dots allow real-time, multicolor tracking of individual proteins with exceptional brightness and stability. It's like using microscopic neon lights that don't fade, each tuned to shine a specific color depending on its size. In biomedical applications, zero-D materials enable diagnostics, drug delivery, photothermal therapy, and targeted imaging by penetrating biological barriers and achieving cell-specific targeting through surface modification. Quantum dots can function as contrast agents, drug carriers, or photothermal agents depending on their functionalization and core composition. Indium phosphide quantum dots are used for in vivo imaging with reduced toxicity compared to cadmium-based dots. It's like sending a fleet of tiny glowing couriers into the body, each carrying a message, a medicine, or a heat burst to the right address. Nanoparticles and quantum dots offer high surface reactivity, active catalytic sites, and tunable electronic structures, making them effective catalysts for chemical reactions and energy harvesting. Applications include water splitting, CO2 reduction, fuel cells, and photocatalysis. Since semiconductor quantum dots can absorb light and transfer electrons to drive redox reactions, titanium dioxide quantum dots doped with nitrogen enhance visible light photocatalysis for environmental remediation. It's like training a tiny army of efficient chefs who work faster, cleaner, and only activate under specific lighting conditions. Zero-D materials are key to future nanoelectronics and quantum information processing due to their discrete energy levels, high charge mobility, and potential for room temperature quantum behavior. They are used in single electron transistors, memory storage, and as quantum bits in quantum computing architectures where electron confinement in quantized states is critical for quantum tunneling and spin-based logic. Colloidal quantum dots integrated into thin-film transistors enable flexible, printable electronics with enhanced optical sensitivity. It's like placing electrons in digital egg cartons where each well corresponds to an on/off state in a next generation logic device. In environmental and sensing applications, quantum dots and nanoparticles detect heavy metals, toxins, gases, and biological markers because their optical or electrochemical properties change upon binding target analytes, enabling highly selective and rapid detection. Sensor arrays can be designed for multiplexed environmental monitoring. Fluorescent quantum dots coated with specific DNA sequences detect mercury ions in water with picomolar sensitivity. It's like a security system with color-changing tiles that glow when the wrong chemical intruder steps on them. Despite their promise, 0D materials face challenges, including toxicity, especially for heavy metal-based dots, scalability of production, and long-term environmental impacts. So, future efforts focus on developing non-toxic, biodegradable alternatives and integrating 0D materials into multifunctional systems. Convergence of AI, microfluidics, and green chemistry may accelerate design of safe, smart nanomaterials. Carbon-based quantum dots synthesized from natural sources like orange peel show biocompatibility and tunable photoluminescence. It's like reinventing the building blocks of light using edible Lego, strong, colorful, and safe enough for both industry and the body.